All right. So today is day 12 of the calculus class. This is going to be video 1 of the applications to derivatives series. The reason this slideshow says day 12 is because it's day 12 of the class, and the last one said day 7 because I made that for day 7 of the calculus course, but we ended up taking multiple days to cover the material. So day 8, day 9 was also on that slideshow. So don't worry about the jump from day 7 to day 12. This is still the next video in the series. Don't worry. So today we start Unit 4. It's a natural continuation of Unit 3. We're just going to be talking about applications to derivatives. Unit 3 was all about derivatives, what they are, and how to calculate them. Today we're going to be learning the uses of derivatives and how we can use them to solve problems and do some cool stuff, hence the name applications of derivatives. So Unit 4, here we come. All right, so today we're going to be talking about the following things. As always, I have to say this, but I just want to make sure that we all remember that I wouldn't expect you to know what these are just yet. I just want you to be able to know them by the end of the lecture. So if you have no idea what these terms are, as I read them right now, don't worry about it. We're going to be covering them. I just want to outline what we're doing so you can at least get a feel for what we're doing. Even if you don't know what they are, I just like to outline what we're doing just so we have just so I'm outlining the plan at least, even if we have no idea what that is. So with that disclaimer out of the way, today we're going to be talking about absolute extrema, the extreme value theorem, local extrema, differentiating between absolute and local extrema. And differentiating in this case does not mean derivatives. It just means the actual
They're literally differentiating.
the common way we would use the word differentiating, in real life, like how to tell the difference between. So that differentiating does not mean, actually derivatives. It means like figuring out the difference. So we're going to talk about critical points, the mean value theorem, what an existence theorem is, and we have to talk about that because the mean value theorem is an existence theorem, and we'll talk about that when we get there. We're going to talk about applications of the mean value theorem and some final theorems and thoughts. There's going to be a couple theorems at the end, but they're pretty self-explanatory, and they're all pretty self-explanatory and pretty intuitive. So I'm not too concerned about covering 3 or 4 mini theorems because they all are really intuitive. And at the very end, we're gonna talk about. I forgot to mention we're gonna talk about antiderivatives, but that just goes along with some of the final theorems, and that's a topic that is a nice segue into Unit 5. They teach it in this unit, and I didn't want to hold it off until Unit 5 because I thought it'd be cool to at least introduce the idea here. But it's not Unit 5 yet. It's just a nice preview for what Unit 5 is going to be like because we're going to be talking about antiderivatives a lot in Unit 5. But more on that at the end of the lecture. All right, we all set? Cool. So some terminology, and we have a textbook definition, but I'll explain my definition first, and then we'll look at how the textbook definition, which explains things in a really complicated way, matches my definition. All right, so the highest function value, and remember the function value is just the y-coordinate, the highest y-coordinate that a function takes on is its absolute maximum value. Pretty self-explanatory and intuitive, right?
Yeah.
Cool. So, for example, if the highest height that a graph reaches is 12, all right, then we'd say the absolute maximum value is 12. We just say that the value is 12. We just give it a number. And yet again, function value and y-coordinate mean the same thing because we consider the y-coordinate, the function, the height of the function. Jesus, my dog is like growling at something outside. Callie. So yeah, when we say function value, that's the same thing as y-coordinate, and the highest function value that a function takes on as a whole is called the absolute maximum value for intuitive reasons. Same with minimum values. The lowest function value, yet again y-coordinate, that a function takes on is its absolute minimum value. We call these points the global maximum or minimum, or the absolute extrema of a function. Absolute meaning yet again, absolute just means absolute, because we're talking about the highest function value or the lowest function value, we're talking about the absolute highest or lowest value.
Yeah.
Right? And extrema, it just is the plural for extreme, because the minimum and maximum are the extreme values of a function, right? The ones that are lowest and highest. So we call them absolute extrema because of that. They're the absolutes, as in they're the highest and the lowest, the definitively highest and lowest, and extrema because they're the extremes of the function. They're either the highest or the lowest.
Yeah.
So that makes sense. That's why we call them absolute extrema. All right. So are you fine with the definition? Like, don't worry about the textbook definition. We'll get that in a second. Are you fine with the definitions I've outlined?
Yeah, absolutely.
Cool. So the textbook defines it in a really mathematical way, but it's really the same thing I'm saying. It's saying let f be a function with domain D. All right. That just means we're dealing with some function that has some domain. All right.
Yeah.
Then the function value at some point, all right, is the absolute maximum value if the function value there is greater than all of the other function values.
Okay.
And it says for all x and d, that means that this is true regardless of what the x value is. If x is in the domain, then the highest point will always be greater than any other function value.
Okay.
So it's a really stupid mathematical way. I say stupid. I don't mean to bash math. I love math, but I mean it's a very extra way to say what I outlined. A function, the function value at a point is the absolute maximum value if the function value there is greater than all of the other function values of that function.
Mm-hmm.
All right, and it's the absolute. And similarly, f of c, the function value at some point c, is the absolute minimum value on its domain. That's what it means on D. If the value there, f of c, the value at that point, the function value or the height, is less than the function value at every other point.
Okay.
So do you see how that matches the definition I provided above?
Yeah.
Cool. And is the textbook definition a little confusing, or does it make sense?
Like a little bit. Like if I read it without you telling me first, I would have been like, "What the fuck is this?"
Yeah, exactly. So it just when it says D, that just means it's domain. So all the possible x coordinates. All right.
Yeah.
So
yeah, but I totally get it.
Okay. Now if you get it now, it's cool. So I like to include textbook definitions and walk through them because like on their own it might be hard to understand what it's saying. But if we walk through it and I give the I think the simpler definition at first, and then we walk through what the textbook is saying, we can understand what the textbook is saying and understand that it just means what I said in a more mathematically sound way.
Yeah.
So yeah, that's the textbook definition. But if it doesn't make sense, everything I outlined before is all you need to know.
Okay.
Cool. All right. Absolute extrema can happen at a function's endpoints or any of its interior points. All right. I'll go to Jamboard to explain. All right. Let's say I had some function, all right, that was defined between x equals -1 and x equals 1. All right. That means the domain of the function, all right, is this. All right. The domain is every number between -1 and 1, including -1 and including 1. Do you remember this bracket notation?
Yep.
All right. So let's say I graph some function that was defined like cosine of x, all right, but its domain was from -1 to 1, all right. So the point I was illustrating before, that absolute extrema can occur at either interior points. Remember, interior points are just the points on the inside of the interval, or endpoints, the points at the end of the interval, is illustrated here perfectly, right? Because the absolute maximum value occurs here, which is an interior point, all right. But the absolute minimum values, there's two points where they occur, right? It occurs here and here, all right? They occur at the function's endpoints.
Yeah.
I will also note that if I ask you to tell me the absolute minimum value, all right, you would just say it's 0, all right? We don't care where it occurs. We just care about what the height is, what the absolute minimum height is.
Okay, right? That makes sense.
Cool. So you wouldn't say like x equals -1, x equals 1. If I ask you what is the absolute minimum value, you're asking what is the lowest height that this graph takes on, and that is 0.
Yeah, okay.
Cool. All right. Okay, next point. An important consideration is that if a function's domain is not closed, then we're in trouble. All right?
Mm-hmm.
Let's look at the same function as before. All right? All right? We have cosine of x, but I'm going to define it as its domain is this interval.
Okay.
What's the difference between this and the other interval I wrote? Let's see if we can.
This one doesn't include -1 and 1.
Okay, so I think you'd agree there is still an absolute maximum value.
Yeah.
All right, and it occurs here. But if I ask you what the absolute minimum value is, what's the problem?
It doesn't really exist.
Yeah, it doesn't exist, right? Because I could choose a number. First of all, it isn't 0 because the function is not defined at negative 1 and 1.
But you can get infinitely close to 0.
Okay, and also, by the way, I will say that this is not cosine of x. I just realized that now. Cosine of x does not intersect the x-axis at negative 1 and 1. So let's just imagine that it's cosine a of x, cosine a times x, such that it intersects the x-axis at negative 1 and 1. So people are probably screaming through their monitors there, going like, "What are you doing, Dylan? It intersects at negative pi and pi." And I'm like, "Well, sorry." So let's imagine this is not cosine of x, but cosine a times x, where the a value makes it so that it intersects at negative 1 and 1. So with that out of the way, we'll note that the absolute minimum value is not 0 because at x equals negative 1 and 1, the function is undefined, so it doesn't equal 0. And if I picked some other number to be the absolute minimum value, let's say I picked a number really close to it, right? All right. This wouldn't be the absolute minimum value because I could always get closer by just getting closer to 1 or negative 1.
Yeah.
All right. So regardless of whatever number I choose, there's always a number that's smaller than it that is defined by this function.
Yeah.
Cool. So there is no absolute minimum value. Because it's an open interval, there is no absolute minimum value of this function.
Okay.
Does that make sense?
Yep.
Cool. So that's just something to be cautious about. Always be considering whether you're dealing with an open interval or a closed interval. Because open intervals you'll have to be very careful because oftentimes they won't have absolute maximum or minimum. For example, I could draw like a parabola that is on this open interval between these 2 points, and it wouldn't have an absolute maximum value. Mm-hmm. Another point is if we had this, let's say this was okay. Before I do the next point, we're all good with this so far, right?
Yeah.
Cool. Let's say I did a half open, half closed interval, right? That would mean that this function includes negative 1 but doesn't include 1, all right?
Yeah.
Now the absolute minimum value exists. It's 0, all right? We don't care how many times it occurs. We know that the function over here reaches 0, and over here it'll never reach 0. So it'll never get to 0 here, but it gets to 0 here. So the absolute minimum value is 0.
Okay, yeah.
So if we're dealing with a half open, half closed domain, we still probably will have an absolute minimum or absolute maximum.
Okay, cool. I'm good with that.
Just be super careful when you're dealing with two open endpoints.
Yep.
Cool. All right, first 2 points, and I want to make sure we understand them, and then we'll move on. All right. Cool. Absolute extrema can occur at a function's endpoints or any of its interior points. That was the first point we talked about. All right. An important consideration is that if the function's domain is not closed, it may not have a definitive global maximum or minimum. That's what we just talked about. All right. And additionally, we talked about this briefly. It is possible for a function to have multiple points whose function values the absolute maximum or minimum. Remember with the cosine function we were dealing with, there were 2 points that took on the absolute minimum value of a function. All right. However, there is still only one definitive maximum or minimum value to the function because we don't really care about how many times it happens. We just care about what the height is, what the lowest height is, or what the highest height is. We don't care how many times it occurs, where it occurs. We just care about what is the highest height the function takes on or what is the lowest height the function takes on. And that's only going to be one number. Doesn't matter how many times the function takes on that lowest height. Does that make sense?
Yeah.
Cool. All right. Lastly, functions with the same defining rule may have different extrema. I don't know why it did extreme. It autocorrects to extreme, I think, because I had that issue yesterday. Has different extrema depending on its domain. What that means is I could have 2 functions, right? Y equals x squared, but its domain was from negative 1 to 1. I could also have y equals x squared, but its domain is from negative 2 to 2. So these functions have the same defining rule, right? The same defining rule that we're taking our inputs and squaring them to get our outputs, but different domains. You agree with that?
Yeah.
Cool. And the first function, all right, is going to look like this. And the second function is going to look like this, all right?
Yeah.
So you'll notice that even though these 2 functions have the same defining rule, the absolute maximum value of the second one is 4, and the absolute maximum value of the first one is 1.
Yeah.
So functions with the same defining rule but with different domains, it's possible for them to have different absolute maxima or minima.
Okay.
So you cool with that idea? Cool. So yeah, functions with the same defining rule may have different extrema depending on their domains. Just be careful.
Cool.
All right. Any questions on that so far?
Nah, I'm all good.
Yeah, a lot of that is just terminology and introducing some concepts. So it's a drag, but we're gonna get to the fun stuff later.
Yeah,
all right. So the extreme value theorem. If f is continuous, I'm just gonna say it and I'll explain it. If a function is continuous on a closed interval, if a function is continuous between 2 points, I'm trying to imagine that in your head. All right. And this interval is closed. Notice that it's a closed interval, meaning it includes the endpoints and doesn't, and includes both endpoints. That's going to be a super important consideration. All right. Then then the function has both a maximum value and a minimum value on that interval.
Okay. Yeah.
And it seems self-explanatory. And it is self-explanatory. We just got to remember that if a function is continuous, all right, between 2 points, all right, and it includes those 2 points, then we'll have an absolute minimum value on that interval and an absolute maximum value on that interval.
Yep. Okay.
Why is it vital that it must be a closed interval and not an open interval?
Because if it's not, then it doesn't exist.
Exactly.
It can get infinitely close to that number.
Yeah, exactly. Then it's because if it was an open interval, it'd be possible for there not to be an absolute maximum or minimum.
Yeah.
All right. So this, if it's closed, it will always have an absolute maximum or minimum. And it doesn't always have to occur at the endpoints either, right? We could have like this, like here's point A, here's point B, and our function goes like this, right? The absolute maximum or minimum value occurs here, and the absolute maximum value occurs here. It doesn't occur at the endpoints, but it still exists, all right?
Yep.
So it doesn't have to occur at the endpoints, but it's just saying if we have a closed interval between 2 points, then there's going to be a maximum value on that interval and a minimum value on that interval. But it has to be closed because if it's open, then there's a possibility that there will be no maximum or minimum.
Yeah.
Cool?
Yep.
Does that sound pretty self-explanatory?
Absolutely.
All right, awesome. The reason we have to outline the closed and open, because you would think that it was self-explanatory without that, but we have to remember to think twice about it, because we had to outline the fact that if it's an open interval, it might not exist, because otherwise our intuition might skip over it, right?
Yeah.
But yeah, so I'm glad that we got that down. Cool. All right. Okay, that's the extreme value theorem. All right, good so far? All right. This one is don't read the textbook definition yet. It's going to confuse you. Sometimes a function's value at a point is still bigger and smaller than the other points nearby. This point could be an absolute extrema or not. We call the function values at these points local maximums or local minimums. What I mean by this is the following. Let's say I drew some function between 2 points, A and B, that looks like this. All right?
Yep.
Cool. The absolute minimum occurs here, and the absolute maximum occurs here. You'd agree? But still, at this point and this point is still lower than all the points near it.
Okay.
Even though it's not an absolute maximum or minimum.
Okay.
Here, this point is still higher than all the points around it, right?
Yeah.
Even though it's not the absolute maximum or minimum.
Yep.
So we call these we call this a local minimum.
Okay.
And this a local maximum for obvious reasons. Local means around it.
Yeah.
And maximum means maximum or minimum. So local minimum means it's the minimum locally, like around it, it's the lowest value. And here, local maximum means around it is the highest value. This is also a local maximum right here.
Okay. Yep.
Cool. Same here. The endpoints, right? If we included the endpoints, right? This would be a local minimum. And this would also be a local minimum. Do you see that? Because in the interval that the function is defined, all the points around the endpoints are higher than the endpoint itself. So the endpoints would be local minimums, even though they're not lower than the absolute minimum, they're still lower than the function values around it. So we call them local minimum still.
Cool.
All right, cool. So that's an important term because it's possible to have things that are local maxima or local minima, but they're not the absolute maxima or minima.
Yeah.
Cool. And also, I will note that absolute maxima and minima, I like saying that. It makes me sound so fancy. Absolute minima, that's just the plural of minimum,
Nice.
are also local minimums. All right. Even though this is the absolute minimum value of the function, it's also a local minimum value, right? Because it's still lower than all the points around it.
Yep.
So the absolute minimum value will also be a local minimum.
Cool.
Same with an absolute maximum. It'll also be a local maximum.
Okay, perfect.
It's kind of like saying like a rectangle, a square is a rectangle.
Yeah, actually, I was just thinking that. I
but
was just thinking about that.
But a rectangle is not a square, right?
Yeah.
An absolute maximum is a local maximum, but a local maximum is not always a absolute maximum.
Yep.
Cool. And we cool with that?
Yeah, I'm totally good with that.
Okay, cool. So I'll read this out and I'll read the definition again in the textbook. It's confusing, but it's if you explain it, it'll make sense. Sometimes a function value is, I think I read this already, but I'll explain it again, is bigger than smaller than all the other points nearby. This point could be an absolute extrema or not, right? Although if a function's value is bigger or smaller than all the points nearby, it could be an absolute extrema or it could not be, like we outlined before, right? Yeah. We call these function values local maximums or local minimums because they're greater or less than the function values nearby it.
Mm-hmm.
And local minima or maxima, they could be an absolute extrema, but most of the time they're not.
Okay.
So yet again, if you see a local maximum, that doesn't automatically tell you that you have an absolute maximum.
Yeah.
All right, so the definition the textbook gives is this. Let C be an interior point. That just means we're picking some x-coordinate C, all right?
Mm-hmm.
Then the function value at that point, all right, f of C, the height of that point, is a local maximum value if the function values around it, that's what this means, are less than the function value at that point.
Okay.
So it's a really complex way of saying what I said. Do you see how this is a mathematical way of saying what I said?
Yeah.
Cool. Same here. It's a local minimum value at our x-coordinate C if the function value at C is less than or equal to the function values around it.
Mm-hmm.
And it says for all x in some open interval containing C. It's really stupid. That just means for all of the x values around C. Yeah. So it's really a complex way of saying what I said.
Okay, cool.
Similarly to what I said before, a function f has a local maximum or local minimum at an endpoint if the appropriate inequality holds for all x in some half-open domain interval containing C. That's a complex way of saying what I said before. Remember when we had our endpoints, right?
Yeah.
It's only greater than or less than the function at one side of it, right? So it's basically saying the inequality we outlined for the previous definition holds, but it only holds for some one-sided interval, right?
Yeah.
Because there's nothing on this side, so it has to be greater than all of the values to the right of it. Here it has to be greater than all the values to the left of it. Whereas here, it has to be less than the value on this side and this side. So all the last, right? If for this to be a minimum, it has to be greater than the ones over here and the ones over here, right?
Yeah.
But for this to be a minimum, it only has to be less than the ones on this side because there's nothing on this side.
Okay, yeah.
We cool with that? So all the caveat at the bottom is saying is that if you have an endpoint, we use the same definition. It just has to be less than or greater than the function values to one side of it. Half open domain. Yeah. Does that make sense?
Yeah.
Cool. I hope it's helpful looking at the textbook definitions. They seem complicated at first, but then going through them and going like, oh, I understand them now.
Yeah. I think it is good. Like you explaining it first and then seeing the textbook definition.
Yeah, I want to keep doing that because I want to show you that even though the textbook looks complicated, when it's explained, it makes sense. Okay, cool. Just some more terminology. Local extrema are also called relative extrema. I hope that makes sense. If not, I can explain it. Just like, relative around it, it's an extrema.
Yeah.
And yeah, local minimum or maximum, the same thing. We call them local extrema as well. Like locally, they're the extreme values. Yet again, what I said, an absolute extrema is also a local extrema for obvious reasons. If an absolute extrema is bigger or smaller than all other function values on a function's domain, then of course it'll be bigger or smaller than the function values nearby.
Yeah.
Okay. Therefore, if you have a list of all local extrema, right, you were able to find all of the points where local extrema occur, all right?
Yep.
One of them will be the absolute maximum value, and one of them will be the absolute minimum value if they exist. It's like a Where's Waldo. It's like if you have a list of local extrema, right, all the local extrema, then the absolute maximum or minimum value, if they exist, will be hidden in there, because an absolute maximum and minimum are also local minima and maxima. Cool. And I'll illustrate the if they exist part, why that's important. All right. All right. Cool. All right. So let's say we had an open interval between A and B. All right.
Yep.
All right. So and it's open, right? Here's all of the local extrema. I'm marking it out, right?
Yep.
Would you agree?
Yep.
Cool. All right. These are the only local extrema that exist, right? Because we can't say this is a local extrema because it's open, right?
Yep.
And we can't say this is a local extrema because it's open, right? So in this case, the list of all possible local extrema will not contain the absolute maximum or minimum value because it doesn't exist.
Yeah.
Right?
Yep.
Because this over here is where it's the lowest and over here is where it's the highest, but it's an open interval, so it doesn't exist.
Yeah, no, that makes perfect sense.
So the caveat is the list of all local extrema will contain the absolute extrema only if they exist. Okay. If the absolute extrema do not exist, then the list won't contain it. And here's an example of that being true.
Okay, yeah.
We cool with that?
Yes.
Awesome. Cool. Okay. And this is what I said before. Local extrema are not always absolute extrema, right? Just because you have a local maximum doesn't mean it's the highest value the function will take on. We cool with that?
Yeah.
Cool. Any questions before I move on?
I think I'm all good.
Any more? Any slides you need to go back to take notes, or are you feeling good?
No, I think I'm all good. Thanks.
Cool. Awesome. Critical points. All right. A critical point is a point in the interior of a function's domain. All right. So if we're not talking about the endpoints of a function's domain, we're talking about the interior of a function's domain. Right. Okay. Where the derivative is either 0 or it does not exist.
Okay.
So if we're looking at this, right, if we're looking for critical points, all right, we don't consider the endpoints, right, because it says we're talking about the interior of a function's domain.
Yep.
And critical points are either where the derivative is 0 or does not exist. So the critical points here would be here. Here's where the derivative is 0. Here's where the derivative is 0. It's flat. Here.
Okay, where the derivative is 0. Gotcha.
Yeah. Here is a critical point because the derivative does not exist.
Yep. And
here is also a critical point because the derivative does not exist here. And if you haven't read the next point yet, don't read it. I'm going to ask a question. If you have, that's fine.
I have not.
Okay, cool. All right. So just look at the picture below. All right. Why do you think I'm bringing up the idea of critical points? What do you notice about all of these critical points? Here's a critical point. Here's a critical point.
Some of them are. Oh well, they are all local maxima or minima.
Exactly. And we're going to read the next point. You aced it. Local and absolute extrema will only occur at critical points or endpoints. Okay?
Yep.
So if we're talking about the interior, notice how the local maximum or local minimum will only occur when the derivative is 0 or doesn't exist.
Okay.
You agree with that?
Yeah.
And also, the absolute or local extrema could also occur at endpoints, right? Like here's the absolute maximum value, right?
Yeah.
And the derivative is not 0, nor does it. The derivative is not 0 and it exists, right? Because when we're talking about endpoints, we calculate the left-hand derivative.
Yeah.
So this is not a critical point, but it's still the absolute maximum value. So when we're looking for local and absolute extrema, we still have to consider the endpoints as well.
Okay, word.
Because this is the absolute maximum, and this is also a local minimum, right? Because all the points around it are bigger than it.
Mm-hmm.
So critical points will tell you where local extrema exist on the interior of a function's domain, but you also have to consider the endpoints. So it's a two-step process.
Okay.
We're going to talk about how to find like extrema in a second, but the process will be look for where all the extrema are in the interior, right? So basically find all the critical points, all right?
Yeah.
And then look at the function's endpoints. You have to look at the function's endpoints and see whether they are maxima or minima or not.
Yeah, okay.
Does that make sense? Any questions?
All set.
Cool. And do you like the visual illustrating why critical points will be where maxima and minima occurs? And minima and maxima, they only occur at critical points. They will not occur anywhere else. If the derivative is not 0, right, then it's going to be going downwards or upwards, so it won't be a minimum or maximum.
Yep.
And also, if the derivative is undefined, it's possible for it to jump down like this. So it's possible if the derivative is not defined for there to be a maximum or minimum.
Yep.
Okay. Awesome. You're doing great. All right. An error of caution. While a function's extrema will only occur at critical points or endpoints, this does not mean that all critical points or endpoints signal the presence of an extreme value, either local or absolute. This is the same thing. Like a rectangle is not a square, but a square is a rectangle.
Exactly. Yeah.
Yep. So notice here's the graph of. I just took a screenshot from Desmos. Here's the graph of y equals x cubed. Mm-hmm. Notice that this is a critical point, right? Because the derivative is 0.
Yeah.
But it's not an absolute minimum because the values to the left of it are lower, and it's not an absolute maximum because the values to the right of it are higher. Yeah. So this is neither a local minimum, local maximum, absolute maximum, or absolute minimum. None of them.
Yeah.
But it is a critical point. So
Absolutely.
Just because there's a critical point does not mean that it is necessarily a maxima or minima.
Okay, perfect.
Maxima or minima will only occur at critical points. But that doesn't mean that every single critical point you find will have a maximum or minimum.
Absolutely.
Cool. Same here. The derivative doesn't exist here, right?
Yeah.
It's a vertical tangent. But is it a local maximum or minimum?
It is not.
Exactly. So just because you find that a critical point exists somewhere does not mean that it is necessarily an absolute maximum or minimum.
Mm-hmm.
That being said, all maxima or minima will occur at a critical point. Do you get what I'm saying here?
I fully get it. Yeah.
Cool. Awesome. So I hope this is a good visual to show why not all critical points are maxima and minima.
Yeah, that is good.
Cool. Awesome. All right. How much longer do we have before the meeting time's out?
I think it says 2.5 minutes.
Okay, awesome. So we just covered 4.1 of the textbook.
Let's go.
All right. And when we get to modeling and optimization, we're going to continue the idea of absolute extrema and local extrema. But how are you feeling with 4.1?
Super good. Super confident.
Good. Awesome. So that's 4.1. The next chapter is 4.2, which is really short. And because we're at a good ending place, I might just end the meeting and restart it to start the next topic. But the next topic talks about the mean value theorem, which we'll talk about when we get back. So yeah, that's 4.1. I'm going to end the meeting. I'm going to end the video. And then Henry, you and I will talk when we come back. We'll see if we need a break and stuff. But for YouTube, the next video you see will be talking about the mean value theorem. So awesome.